Hello everyone, my name is Bizhao Pang from the Air Traffic Management Research Institute at Nanyang Technological University, Singapore. Today I will present our work, Constrained Multi-Agent Reinforcement Learning with MAF-Net for Safe Trajectory Planning. We start from the application problem in air transportation domain. Thunderstorm cells can evolve quickly and block nominal flight paths. When this happens, aircraft needs to reroute in real time. This is not only a single-agent planning problem. Multiple aircraft may be affected at the same time, and each aircraft must avoid both the thunderstorm cells and the other aircraft. Therefore, one aircraft decision can change the feasible actions of the others. This makes the problem a dynamic, multi-agent decision-making problem with safety constraints. The goal is to learn decentralized policies that can make safe, coordinated, and scalable decisions using local observations. The main point of this slide is that moving thunderstorms create a coupled decision-making problem. We need each aircraft to act locally, but the overall behavior must still be safe and coordinated. Existing methods in this domain face three main limitations. First, optimization and sampling-based methods are often interpretable and can generate feasible trajectories. However, they are hard to adapt in real time when the environment changes quickly, and they may not scale well in dense multi-agent settings. Second, reinforcement learning methods are more adaptive, but safety is often handled mainly through reverse shaping. This means constraint violations can still happen during learning or execution. Third, recent action masking methods can improve safety, but many of them use hard masks or focus on discrete action spaces. This can interrupt gradient-based learning, especially for continuous control tasks. Therefore, we need a decentralized multi-agent learning methods with differentiable safety-aware action filtering. To address this gap, we propose IDDPG-MAF. The first component is IDDPG, an independent deep deterministic policy gradient. Under the centralized training and decentralized execution framework, agents are trained with centralized information, but each agent executes its policy using local observations and outputs a continuous heading change action. The second component is a time-dependent action mask. At each time step, it classifies the action space into three regions: unsafe actions, desired actions, and undesired but still safe actions. The third component is MAF-Net, a pre-trained multi-head action filter network. It takes the raw actions from the reinforcement learning policy and filters it before execution. The key point is that this filtering is differentiable, therefore it improves safety while still preserving gradient-based policy learning. This slide shows the detailed design of the MAF-Net. Its input includes the local state, the rule actions from the RIL policy, and a time-dependent action mask. MAF-Net has three heads. Head 1 projects unsafe actions to the nearest safe action. Head 2 preserves desired actions. Head 3 corrects undesired actions towards the designed heading direction. After pre-training, MAF-Net is frozen during reinforcement learning process. The filtered action is executed in the environment and stored in a replay buffer. The key benefit is that MAF-Net separates safety filtering from policy learning, improving safe exploration while preserving gradient-based updates. Now let's look at how IDDPG-MAF is trained. We use a centralized training and a decentralized execution framework. During training, the critic can use global information to evaluate joint behavior. This helps the agents learn coordination from shared reverse and safety costs. During execution, each aircraft only uses local observations. The actor outputs a continuous heading change action. Before this action is executed, it is passed through MAF-Net. It outputs a filter action, and this filter action is used in the environment and then stored in a replay buffer. The policy is then updated by considering both reward maximization and safety constraint penalties. The results on the right show the effect of this design. IDDPG MAF achieves faster convergency with lower variance than the baselines, and the loss of separation rate remains below the risk threshold of epsilon equals 0.01. We compared the proposed methods with two groups of baselines. The first group indicates trajectory planning and reinforcement learning baselines for aircraft rerouting, including fast matching train, DDPG and IDDPG baselines. Those methods represent sampling-based planning, centralized reinforcement learning, and decentralized multi-agent reinforcement learning. The second group is the safe reinforcement learning baseline, IDDPG CBF, control barrier function. Since there is no ready-made safe reinforcement learning baseline for this exact task, we designed control barrier function constraints for aircraft separation and storm avoidance and integrated them with IDDPG methods. The results shows that IDDPG MAF maintains near zero loss of separation and 99% goal reach rate as aircraft density increases. Compared with IDDPG CBF, MAF-Net is less conservative. Instead of projecting actions online using a control barrier function, it learns a differentiable action filtering mechanism. This leads to better scalability and more reliable task completion. We further evaluated scalability, robustness, and the contribution of each MAF-Net component. For scalability, IDDPG MAF is tested from 5 to 45 aircraft across large airspaces. It maintains around 99% goal reach rate, showing stable performance as traffic density increases. This efficiency doubles the maximum capacity compared with the current practice in this setting. For robustness, we introduce position uncertainty. The model still maintains 95.5% goal reach rate under moderate level of position errors. Performance starts to degrade when uncertainty increases to larger than or equal to 0.8, which indicate the reliability boundary. For ablation, the full MAF-Net shows the most stable learning. This confirms that the three heads have complementary rules, projecting unsafe actions, preserving desired actions, and correcting undesired actions. We demonstrated the methods in the next three slides. These slides visualize the learned policy under increasing agent density. We tested cases from 48 aircraft under dynamic weather and crossing routes. Further demonstrate the generalization across unseen route structure. The model is evaluated on route structures that are different from those used in training. We tested different number of aircrafts under those new traffic patterns, and the results show that the learned policy can maintain safety and coordination beyond the original training layout. We then demonstrated the robustness to different weather configurations. We test a different storm size and a different number of storm cells. The trajectory shows that the proposed methods can adapt to those dynamic weather configurations while maintaining safe and coordinated rerouting behavior. To conclude, we propose IDDPG MAF, a constrained multi-agent reinforcement learning method with a pre-trained differentiable action filter. In our experiment, the proposed methods achieves no more than 1% loss of separation and a scalability to 45 aircrafts in the tested scenarios. More broadly, MAF-Net can be used as a safety-aware action filter for other real-time multi-agent systems. There are limitations. The current setting considers only two-dimensional fixed flight level rerouting, so the vertical maneuvers are not included. Also, performance degrees under high position uncertainties. Future work can consider adaptive risk buffers, uncertainty-aware filtering, and human-in-loop validation. That's all for today's presentation. Thank you very much for your attention. Please feel free to contact us if you have any questions or suggestions on possible extension of this work. Thank you.